Hey guys, it's Mrs. Herbst. I am recording from home, so if you hear puppy sounds or baby sounds, that would be why. I'm also experimenting with a program to do these recordings, so you'll just have to kind of bear with me. If we don't like it, we'll do differently next time. So we're going to go ahead and start with our review chapter. It's called Chapter P, and it's a review of some of the things you would have done in pre-calc, Algebra 1, Algebra 2, geometry, just kind of refresh ourselves so that we can add to it as we go into calculus. Normally, this would be the stuff you would have done your summer assignment on, but obviously things have been odd. So we are doing P1, which is graphs and models. It'll start off pretty basic. So we're going to sketch the graph of y equals x squared minus 2. There's several different methods we could use. You could use ordered pairs. So you could do, if you wanted, just do an XY chart. You could plug in different numbers. You do know what this shape is going to look like, so you'd want to make sure that you have enough points to get your U shape. If you didn't know that x squared is quadratic, it'd have a U shape. So I would go along with things like -2, -1, 0, 1, and 2, just to get that shape, hopefully. And if you don't get your U shape, you can always add in more points. And so if we go in and plug those points in, remember you're plugging them into the equation y equals x squared minus 2. So if I plug in -2 and I square it, I get 4. 4 minus 2 is 2. Plug in -1, I get 1. 1 minus 2 is -1. Plug in 0, get -2. Plug in 1, -1, and 2. If you're not sure how you got those, we just plug those numbers in for x right here. All right, so then I can just plot those ordered pairs. So -2, up to, and so on and so forth. So I'm not going to go any farther into that because I want you to see the other options. But you could get that U shape from that. Transformations would honestly be the easier way. Since you know this is U-shaped, or should know it's U-shaped, it's just been shifted down to from a typical parabola. So instead of the vertex of the parabola being here, okay, it's going to be down to. Okay, so remember those transformations outside the function, those are moving it along the y-axis up and down. Anything inside the function using parentheses, that'd be left and right. So remember that. You can also use your graphing calculator. This is AP Calculus. You will use our graphing calculators a lot. Part of the AP test is calculator based. So you would be able to use your calculator to shortcut some things. So you could do that. So we can get this shape pretty easily. Go ahead and graphing that. You could also use symmetry, which is something I'll talk about later. And parabolas do have that symmetry. Through their vertex. If it's not been shifted left or right, it is symmetric about the y-axis. So there is that graph. But you can use any of those forms. I recommend being able to use your calculator to check and points or transformations to initially do that. You don't always get your calculator. All right, so we're going to talk about a couple of different things. We are finding the intercepts of graphs. So this will be a super useful skill throughout the semester. So in order to find x-intercepts, okay, you'll just let y equal 0. If you think about where an x-intercept is, where it crosses the x-axis, okay, that means it has no height. So the y has to be 0. Okay, so you're going to get an ordered pair like x comma 0. Y-intercepts, just reverse the concept. If it's going to cross the y-axis, you're going to be having 0 be your x value because it's not going to be shifted left or right. And so we just plug that in. So this is not asking us to graph it. Be careful, read directions. Don't do more than you need to. We're just going to find the x-intercepts and the y-intercepts of this graph. So if we start with x-intercepts, I like to label everything. You have to bear with my handwriting, guys, because I am writing on a computer. It's a little strange. But what we're doing is we're just going to let y equal 0. So 0 equals x cubed minus 4x. And then you have to find the values for x to be able to get those x-intercepts. So what I'll do is I'll use some of my Algebra 1 skills, and I will just factor out an x this way. And then if you notice, I can factor it once more. If you notice that x squared minus 4 is the difference of two squares, you vaguely remember that from Algebra 2, maybe Algebra 1. If you have your first term squared and your second term squared and the operation in between a subtraction, you can split it into square the first, square the second, different signs in the middle. So then once you have this, we use our zero product property. Most people don't know the name of that, but if I have things multiplied together equal to 0, I can set each thing equal to 0. So I can do my x is equal to 0, my x minus 2 equals 0, my x plus 2 equals 0, And I can solve them all. So this one's already solved. This one gives me x equals 2. This one gives me x equals -2. You can leave them like that as x-intercepts, or you could write them as an ordered pair, like 0, 0, 2, 0, -2, 0. So for y-intercepts, on this case, it'll just be a little bit easier on us, less work, is I'm going to let the x's be 0. So y equals 0 cubed minus 4 times 0. I try to, when I plug in numbers, especially if they have the potential to be negative, put parentheses. But here it's pretty straightforward. If we have 0 minus 4 times 0 is 0. So my y-intercept is 0. And again, you could do that as an ordered pair. Again, if you have any questions on some of this review stuff, make sure you ask or Google it or use Khan Academy. It's a matter of you have to remember this stuff because calculus is algebra 1, algebra 2, geometry all combined together. Okay, it's called analytical geometry for a reason. All right, so this one, we don't have an example to go with this exactly, but it's important to be able to test for symmetry. So if you picture the graph of parabola, it's a perfect U. So it does reflect. Okay, now if it's not shifted left or right, it might have symmetry about the y-axis because the left side to the y-axis is going to match the right side to the y-axis. So the y-axis symmetry is if I have a point x comma y on my graph, then it also will have the point -xy because it's reflected across that y-axis. Okay, if you look here, I've drawn a little arrow. You can test for that by just plugging in -x. Okay, if when I plug in -x, it matches what it was before exactly when it's simplified, then it must have y-axis symmetry. If you go to x-axis symmetry, you might picture maybe a parabola that's an x equals parabola with a y squared. So that means it's opening to the left or opening to the right. Okay, same thing kind of goes. If it has the point xy, then the graph will have the point x -y because it's reflecting across that x-axis. Likewise, I can plug in my y value to be negative, opposite of whatever it is. And when I simplify it, it will go back to the way it was again when I plugged in the -y. And that means it has that x-axis symmetry. Origin symmetry would be the fact that everything's rotated. So you kind of picture a cubic function. So like y equals x cubed, it would have origin symmetry because when I plug in -x and -y, I'll do both of them for my test for symmetry, then it results in exactly the way it was when I simplify and do some simple algebra. One thing to remember is a graph at most has one type of symmetry. It doesn't have to have any symmetry. It cannot have both, though. I can't have something that's origin symmetry and axis symmetry. It's going to be one or the other. Okay, so essentially those symmetries are acting as mirrors. Origin symmetry means it's origin being about the origin 0, 0. Okay, so we're going to do a little example here to practice that. We're going to test the graph of y equals 2x cubed minus x for symmetry with respect to just two of them, y-axis symmetry and the origin. So in order to do y-axis symmetry, if you go back to our instructions, it says y-axis symmetry means I'm going to plug in -x for x. So then I go back here. So I'm going to rewrite this equation, y equals 2, but in place of x, I'm going to put -x. And in place of x again, I'm going to put -x. And then I'm just going to simplify. If it didn't change a thing once it's simplified, then it has to have the symmetry. If it does change something, it doesn't have the symmetry. So I'll go ahead and simplify. -x cubed is -x times -x times -x. I have 3 negatives, so it stays negative. So when I simplify this, I would have -2x cubed. And then a negative times a negative here, that would give me a positive. And so it simplifies to this. And if you look, it changed the signs of both the numbers on the right, didn't change the number on the left, the y. And so this would be not symmetric about the y-axis. Okay, well, then we go try the origin, which means we're replacing both the x and both the y. So in place of y, I write -y. In place of x, I'll do exactly what I did earlier and replace them with -x. And then, left off my negative. And then we will simplify from there. So -y can stay -y. We already know what this right side simplifies to. We did it earlier. So I will just rewrite that. Okay. And then if you notice, there is a change on the left and there is a change on the right, but it still looks different than the original. So what I'm going to do is I'm going to divide everything by -1. That keeps it balanced. So a negative divided by a negative is positive y. And then if I divide the right side by -1, it'll change those signs. -2x cubed divided by -1 is 2x cubed. Positive x divided by -1 is -x. If you look now, it matches that perfectly. So it is symmetric about the origin. So I'll just write origin symmetry. Okay. And if we would have tested for the x-axis, we would have been plugging in -y. And you would have seen too that it changed a lot. So we couldn't use that one. All right, so now we're going to sketch a graph. One of our important skills we'll use through calculus will be able to roughly sketch graphs and more accurately sketch graphs, and the AP test loves you analyzing graphs, so we have to get good at it, so we're reviewing. I did put a hint on here for us. There's a lot of different ways to graph this. We could use the points, we could use our calculator. This one would be a little bit harder to use transformations, but you could use transformations. It's just you wouldn't be using a y equals, you'd be using x equals. What I want to do is I want to use intercepts in symmetry because I think it'll help us a lot. So if we do our x-intercept to start, and then we'll do our y-intercept, and then we'll figure out our symmetry. So x-intercept means I'm going to let y equal 0. So x minus 0 squared equals 1. And if you weren't remembering that, if you go back up to the slide where we talked about intercepts, those instructions are there. So then if I solve that for x, that's pretty easy. We're subtracting nothing, so x is equal to 1. I'm going to go ahead and graph that x-intercept. So I have an x-intercept of 1. Y-intercept, I'll go and let x equal 0. So I have this. I have to get y by itself. Pretty easy considering we have 0, so I have -y squared equals 1. I can't keep that negative there, so I will divide both sides by -1. So I have y squared equals -1. And fun thing about calculus, if we were in algebra 2, we would end up with I, plus or minus I. Awesome thing about calculus, we only deal with real numbers, so we don't have an I here. So there's no y-intercepts, okay, which is not super helpful for our graph, but we don't have any y-intercepts. So keep that in mind. If you're going to get an unreal solution when you're doing something in calculus, there's just not a solution to it. We deal with real numbers, real planes here. All right, and then symmetry, what we're going to do is we're going to test. So if you kind of look at it, you can do a lot of this in your head if you have good number sense, and by the end of this, you will. We'll get better at it. But I want to be plugging in -x so that I could see if I had x-axis symmetry. I want to plug in -y to see if I have y-axis symmetry. And so we do those things, vice versa, sorry, plug in x for y-axis symmetry. And so one thing I would do first is kind of look in my head. If I'm going to plug something in, what's going to change? If I plug in negative for y because it's squared, a negative squared is now positive. And so that would be where I would start. You could always start at the beginning and test for y-axis symmetry, but I would actually test for x-axis symmetry first. Okay, so we're going to plug in for x-axis symmetry -y. So x minus -y squared equals 1. And then I simplify. Again, a negative times a negative, -y times -y is positive y. So I have x minus my positive y squared equals 1, which it didn't change at all, which is why we strategically chose that. So it does have x-axis symmetry. So I know my graph will be reflected across this x-axis. So what the top looks like, the bottom will look like. Again, there's nothing to reflect though. We only have that intercept. So we need another point. So let's just pick an easy point. Say x equals, let's do x equals 2, since we already have x equals 1. And if I plug in 2, I would get 2 minus y squared equals 1, and I would need to solve for y to get that y value. So then I would have subtract 1, add y, and I would have 2 equals y, left off my squareds. And then I would have square root of 2. So maybe I should have chose a different number, but it's not a big deal. Square root of 2 is between 1 and 2. And so we can kind of roughly graph that. It's in here. And since it has symmetry, it's also here. And I have my U shape. Probably a better choice to plug in would have been something like 4. And, oh no, that should have been 1. It would have been 1. Let's see. Undo. So you guys have to bear with me. I haven't done math all summer. All right. And that will graph nicely because we'll have plus or minus 1. Oh, much better. And if we were in class, I would hope you guys would have corrected me on that. All right. So then you can roughly sketch that. Okay, this is one of my favorite things to do. This is really useful. One of the cool things about calculus is we get to work in 3D. I don't know if you guys do much of that in Algebra 2, but a lot of our graphs, we will take regions and rotate them and make three-dimensional figures, and it's really cool. So like we could rotate a semicircle, obviously, and we make a sphere, but we don't necessarily know anything about the sphere. We only know about the semicircle. Knowing the points of intersection is one of our key things to being able to start some of those problems when we get to that point. And it's just an Algebra 2 skill. We just need to review this Algebra 2 skill. So finding all points of intersection of a graph means I need to figure out where they overlap. Okay, so where they share the same points. So lots of different options. You can make them equal to the same thing and then set them equal to each other. So I could solve both for y equal to each other. You can do it by substitution like you did in Algebra 1 where I solve just one for x or y and plug it into the other one and simplify. In this case, if you notice both the y's are degree 1, that means their exponent is 1, they'd be really easy to solve. So if I rewrite both of these to be y equals, in this case I would add y to both sides and subtract 3 from both sides so that I have x squared minus 3 equals y. And then I do that same thing on the other side. I'm going to add y to both sides and I'm going to subtract 1 from both sides so that I have x minus 1 equals y. And if you don't like having y on the right, you can move it to the left. It's not a big deal. Equal signs have the commutative property, so you can rearrange them as you please. All right. So then since they're both equal to y, they have to equal each other. That's called the associative property. So if x equals 2 and y equals 2, since they're equal to the same value, they have to equal each other. That is the same concept we have here. So I'm actually going to plug this whole y in for this whole y. Okay, so they're equal to the same thing. So I'll do x squared minus 3 equals x minus 1. And I just have to solve this. What I'm going to do is I notice I have a quadratic term, a linear term, and 2 constants. I'm going to just move everything to one side because it's a quadratic. That means I can use quadratic formula, I can factor it, I complete the square. You have a lot of options that way. So I'm going to move everything to the left. Just like that. Negative 3 plus 1 is negative 2 equals 0. And I have this here. And so we would need to be careful that we solve this correctly. So to figure out what, you use a quadratic formula, this does factor. So what multiplies to negative 2 and adds to negative 1? Okay, that is that shortcut to factoring this. Instead of doing guess and check or 4-step method, you can do that. And if you're not sure about factoring, that's probably something you're going to need to review because it was taught in Algebra 1. We did it in geometry. You would have done Algebra 2. I know you for a fact you did it in pre-calc, so it's just one of those things that doesn't go away. But what multiplies to your constant and adds to your coefficient of your linear term, in this case negative 1, would be negative 2 only has factors of 1 and 2. So we know it's going to factor into something like this, and we know it's got to be 1 and 2. We have to figure out what sign to give it so that it multiplies negative 2 and adds negative 1. So if I try this, if you look, if I FOIL this out, x times x is x squared. X times negative 2 is negative 2x. And then 1x, when I combine negative 2 and 1x, I get this negative 1x squared, or 1x here. And then negative 2 and 1 multiplied together do give me that. And so then I have x plus 1 and x minus 2 is my factored. It does say find all points of intersection, so that doesn't mean we're done. To find all points, we have to figure out where actually those locations are. So I'm going to use my zero product property again, and I'm going to set each part equal to 0. When we get more comfortable with some of the stuff, we can skip some of these steps because we should be able to solve these in our head because they're pretty easy at this point once it's factored. It does say points again. It's not just the x values, so you would want them written as points, as ordered pairs. So again, I would need to write them as an ordered pair. So I have to figure out where their y values are. all you have to do is plug it into any of the original equations. Easiest one I think to plug it into would be this, because it's already solved and there's no squared. So if I plug in -1 minus -1 is -2. 2 minus 1 is 1. And so then there's your points of intersection. Those are the actual locations on your graph. For your homework, I am going to be putting out a blank answer sheet in Kami for you to write all your work in, and you can submit it that way. We should try to get our homework done efficiently and timely, because it'll help you with your quizzes and it'll help you with your assessments as we get closer to time. We'll try to do 2 videos a week. If you have any questions, please contact me. You can contact me with a remind. You can contact me on Google Classroom. You can contact me through email. But all assignments need to be turned in Kami or they're not going to count. So be looking for that assignment to be pushed out through Kami as soon as possible. And I hope you guys were able to learn or remember a lot. Again, if you have questions, please contact me. And I hope to see you all soon. Bye-bye.